Greetings 345 students. My name's Ryan, and today I'm going to cover the organic separation techniques experiment. Let's begin by talking about the theory behind this lab. This experiment will introduce you to liquid-liquid extraction, which is a technique you can use to separate two or more compounds based on their solubilities. Here's how it works. Imagine you had an aqueous solution of ethanol that was contaminated with benzene, and you wanted to get the benzene out of it. To do this, you could mix your solution together with some organic solvent. Since benzene is more soluble in organic solvents than it is in water, it would migrate to the organic solvent, or organic phase, and therefore remove itself from the water, which we also call the aqueous phase. However, since ethanol is more soluble in water, it would stay behind in the aqueous phase. Now, that's all fine for ethanol and benzene, but what if you're dealing with a compound that can easily lose or gain a proton? For example, hexylamine. When this compound is deprotonated, it doesn't carry a charge and is very soluble in organic solvents, but not so much in water. But if we add a little sulfuric acid to the mix, the amine group will become protonated and, as a result, gains a positive charge. This charge helps the compound interact better with water, and so when hexylamine is in acidic conditions and protonated, it becomes more soluble in the aqueous phase. This concept works for many compounds that have ionizable protons, and you can use it to get these compounds to move to one phase or the other. In this experiment, you will use liquid-liquid extraction to separate a mixture of three compounds from each other. One of these compounds has a carboxylic acid group that takes on a negative charge when the group is deprotonated, which happens when it encounters strong base like sodium hydroxide. Another compound in the mixture has an amine group that acquires a positive charge when it gains a proton, which it will as long as the pH of the solution it's in is relatively acidic. And the third compound doesn't have an ionizable group, so it stays neutral regardless of whether it runs into acid or base. Knowing all this, you should be able to predict which of the two liquid phases, the aqueous or the organic, each compound would migrate to if you supplied them with acid or base. Now let's go over your procedure. This begins, as always, with your PPE. That would be a lab coat, gloves, and goggles. Make sure those goggles stay on the whole time you're in the lab room. As you may have guessed, a big part of this experiment is going to involve mixing aqueous and organic solvents together. However, you're not going to do this in just any old container. Instead, you're going to mix them in one of these, a separatory funnel. These funnels have a valve at the bottom you can use to drain off the lower layer and leave the upper one behind. This will let you separate the two layers, as well as any solutes that are dissolved in them. Note that the lower layer isn't necessarily the aqueous one. This depends on the density of the organic solvent you use. If that solvent has a higher density than water, then the organic solvent will be on bottom. Before you begin, you're going to want to give your separatory funnel a good cleaning. Add some glass cleaner and water to it, then give it a shake, and pour the soapy water out. Then take the valve insert out and rinse the funnel with water. And again with some DI water. Then one more rinse with acetone. Clean the valve insert too before you reinsert it. When you go to reassemble the funnel, put the plastic washer on first, then the rubber O-ring, then the securing nut. When you tighten the nut, leave it loose enough you can still comfortably turn the handle. And don't forget the stopper, gotta clean that too. The next thing you'll need to do is make a solution of the three compounds you will separate. Do this by weighing out between 200 and 250 milligrams of each one, and dissolve them in about 20 milliliters of diethyl ether. After everything has dissolved, add the solution to your separatory funnel. Oh, and make sure the funnel's valve is closed before you add the solution, with the handle perpendicular to the funnel's axis. If you don't, things might get messy. Next, add 20 ml of hydrochloric acid solution and put the separatory funnel's cap on. To help the extraction along, you're going to have to shake your flask's contents. To start, make sure you've got your fingers on the cap to hold it on, give the flask a small shake, then point its spout into the hood and open the valve to vent it. This is to relieve the pressure that builds up during shaking. After the first time you vent it, the pressure buildups won't be as bad, so you can shake it a little longer and more vigorously before you vent it again, which you want to do every few seconds or so. After you've shaken and vented your flask about 5 times, take its cap off and let it sit in the ring long enough for the organic and aqueous layers to separate. As soon as they have, drain the lower layer off into a small Erlenmeyer flask. At this point, it's okay if you leave a little of the aqueous layer in the flask, but try to get as much of it drained off as you can. Next, add 20 milliliters of sodium hydroxide solution to your flask, and again shake and vent it 5 times. Then drain the aqueous layer into a separate Erlenmeyer flask. When you're done doing that, pour the ether out through the top into a pre-weighed beaker. You'll separate the ether in this beaker from any solutes that are dissolved in it by volatilizing the ether off. In other words, you'll heat it and the ether will boil away. Do this by placing a boiling stick in the beaker and gently warm it on a hot plate. The key word here is gentle. You want to apply just enough heat you can see some bubbles coming off the end of the stick, and not much more than that. Now, this is going to take some time, so just be patient and don't try to rush it by getting it too hot. After the ether in your organic extract has finished going away, it will be time to neutralize your acid and base extracts. Neutralize your acid extract by adding about 8 milliliters of sodium hydroxide solution to it. Note that, since the precise quantity of hydroxide solution you add isn't terribly important, you don't have to use a graduated cylinder to measure it out. Since a Pasteur pipette dispenses about a milliliter with each use, just use one of these to give your extract 8 squirts of solution. After you've added the hydroxide and mixed it a little, use a strip of litmus paper to check the pH. If it's not neutralized, add another few mils of hydroxide and check the pH again. Do this until its pH is neutral or a little on the basic side. You'll neutralize the base extract the same way, except you'll add hydrochloric acid to it instead of sodium hydroxide. When you're done with all that, take a good look at your 3 extracts and record what you see in your lab notes. You'll need this information to help you figure out which compound ended up in which extract. By the time you get to this point, the liquid-liquid extraction part of this experiment will be done, but there will still be a few more tasks you'll have to perform. See, part of the point of this experiment is not just to learn liquid-liquid extraction, but to determine how effective it is at recovering and purifying compounds. To this end, you'll need to isolate and dry the solids you obtained when you neutralized your acid and base extracts. And the best way to do this is by vacuum filtration. Here's what a vacuum filtration rig looks like. The funnel on top, a Buchner funnel in this case, holds a piece of filter paper that your extracts will get poured onto, and the hose coming off the side goes to a vacuum source. When you turn the vacuum on, it pulls air through the funnel and helps it filter faster. Get your filtering setup ready by weighing the filter paper, then put it in the funnel and dampen it with a little DI water, and then turn the vacuum on. Slowly pour your extract out onto the paper, getting